Hi everyone, it's Mrs. Summer here to talk about Lesson 303, Conservation of Mass Intro, otherwise known as our Counting Atoms lesson. In this lesson, students will be able to define conservation of mass, count the atoms in a chemical formula, and count the atoms when there is a coefficient. During a chemical reaction, bonds between atoms break and reform. Atoms are not destroyed and no new atoms are formed. And all atoms at the start of the reaction are present at the end. So conservation of mass. Atoms cannot be created, nor can they be destroyed. They can only be rearranged. The conservation of mass states that the total mass of reactants before a reaction is equal to the mass of the products after the reaction. So conservation of mass, atoms are conserved. So in this example, we have magnesium plus oxygen yields magnesium oxide. So here we have 2 magnesium plus O2 yields 2 MgO. And if we draw out our little circles to represent each atom, on here we have 2 Mg, so we have 2 Mgs, and then we have 2 oxygens that are attached to each other. And then when we get over here to the product side, we have MgO and MgO. So on the total on the reactant side, we have 2 total magnesium and 2 total oxygen. And over on the product side, we have 2 total magnesium and 2 total oxygen. It was just that they were rearranged. So in order to show conservation of mass, you must be able to count the atoms of each compound properly. So we have represented coefficients and subscripts. So the subscripts are the little lower number, little lower number to the right of the element it applies to. It tells you the number of atoms in an element in the molecule. So for example, in H2O, how many hydrogen atoms are there? Well, I see this 2, and it only pertains to the thing that comes right before it. So there are 2 hydrogen atoms. And how many oxygen atoms? Well, here there's no subscript, which means that we imply that it's 1, and so there's 1 oxygen atom. So you try this. How many carbon, how many hydrogen, and how many oxygen atoms are there in C6H12O6, otherwise known as sucrose with sugar? So in this 6 goes to the carbon because it comes in front, so there are 6 carbon atoms. This 12 goes to the hydrogen, and there's 12 hydrogens. This 6 goes to the oxygen, and there are 6 oxygen atoms. Coefficients are the normal size number to the left of the molecule it applies to. It tells you the number of molecules there are. So example is 2H2O. So how many total H2O molecules are there in 2H2O? Well, there are 2 in 2H2O. So with coefficients, you distribute the coefficient to find the number of each atom in the molecules. So for example, we have 2H2O. And so we need to distribute this 2 to everything it comes in front of. So how many hydrogen atoms? Well, we have 2, and this is where we multiply. So we have 2 times 2, because of that subscript, equals 4 total hydrogen. Now we have 2 times 1, because there's no subscript next to oxygen. So we have 2 times 1, which is 2. So now you try. Count the atoms for the following examples: NaOH, MgCl2, 4HNO3, and 5ZnSO4. Okay, for the first example, we are NaOH. So Na, there's just 1 O, there's 1, and H, there's 1, because there are no subscripts and no coefficients. For question 2, we have MgCl2. So we have Mg, and there's no subscript or coefficient, so there's just 1 Mg. For Cl, there is a subscript, so we have 2 chlorine atoms. Let me remove that little subtraction or dash because I don't want you to get confused. Then the next example is 4HNO3. So now we have this coefficient and we have some subscripts. So for hydrogen, we have the 4 coefficient and let me use 4 coefficient, and hydrogen has no subscript, which means it's just times 1 equals 4 total hydrogen. For N, we still have the 4 in front and no subscript, so times 1 equals 4. Now with oxygen, we still have the 4 coefficient, and then we have a subscript of 3, which is equal to 12. Now for our last example, we have a coefficient of 5. So we have Zn, and we have the coefficient of 5, and Zn does not have a subscript, so it's just 1. So we have 5 zinc atoms. For sulfur, we have the coefficient of 5, and then we have 1, which is equal to 5. And then for oxygen, we still have the 5 coefficient, and then we have another 4, so we're going to get 20 total oxygen atoms. Polyatomic ions are covalently bonded molecules that have a charge, so they attract to an anion, or, this was the right, or a cation. Or a cation. Polyatomic ions travel together in a chemical reaction. So think about what I was introducing last unit. Polyatomic ions are like a group of girls going to the bathroom. They stick together. So when they react as a group. You do not break them apart. So the parentheses indicate multiple polyatomic ions within a formula. So if there are parentheses, you must first distribute the subscript outside of the parentheses. Then follow our rules that we've already discussed. So here's an example where we have 2 Mg3PO4 2. So we first have to distribute this 2 when we're counting the atoms into everything inside the parentheses. So when we're counting the atoms, for magnesium, we have this 3 and the 2, so we have 2 times 3 equals 6. But for phosphorus, we have to first distribute this 2, so we're going to distribute the 2, and since there's no subscript here, it's just times 1, so 2 times 1, but then we have this 2 coefficient in front. So times 2 is equal to 4 total phosphorus. For oxygen, we have to distribute that 2, but we started with 4 times 2, and then we multiply it again by the coefficient of 2. So 4 times 2 is 8, times 2 is a total of 16 oxygen atoms. And you can do that you can see that by counting up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. You can draw out your molecules to see visually what it looks like. Here's another example where you can visually represent how many total of each atom there are in 4CuNO3. Another example where you can count up and visually see how many of each atom there are in 3AlOH3. So you try. How about you count the number of atoms for each of the following examples. So in this example, we have Mg. There are 4 Mgs. In oxygens, we have 2 times 4 is 8. And for hydrogen, we have 2 times 4, which is 8. In our next example, we have Al, which there are 2 times 4, which is 8. Then we have sulfur, which is 3 times 1, which is 3, times 4, which is 12. And for oxygen, we have 3 times 3 is 9, times another 4 is 36 total oxygens. In this last example, we have N, which is, we have 3 and 1, which is 3, times the 2 out front, 6. Then we have hydrogen. 3 times 4 is 12, times the 2 out front is 24. P, we have 1P, but times the 2 out front is 2. And for oxygen, we have 4 times 2, which is 8. So you try it. Count the atoms for either side of this reaction. So by doing this, aluminum, we have 4 total aluminums. For oxygen, we have 6. Over here, we have 4 aluminums and 6 oxygen. How we can say, yes, the conservation of mass has been applied and is done correctly because we have the same total number of atoms on each side of the yield. Here's another example I want you to try. Count your atoms. So on this side, we have 2 Na and 2 Br. Over here, we have 2 Na and 2 Br. So yes, conservation of mass has been applied. Our last total example, count the atoms on either side of the yield sign. So we have 2 hydrogens, 2 chlorines, and 1 zinc. We have 2 hydrogens, 2 chlorines, and 1 zinc. Now, the reason I wrote my little tables here the way I did is once we get to balancing chemical equations later in this unit, it will be very helpful for you to create this visual where you can see hydrogen and hydrogen and chlorine and chlorine. You can look straight across to see and count your atoms.